Okay. um, I think it just makes more sense to have this in two separate videos because it gets pretty long. We talked about confidence intervals and the fact that we're always a little uncertain in our measurements. And the more confident we want to be, the bigger the target we have to have, right? The bigger the window, the bigger the uncertainty is, right? So let's go back to, let's see here, and we'll play this by going down here. And okay, so we'll go to the next thing here. Now we're going to do some calculations. Okay, now this is going to be for those of you who are just maybe taking Calc 1 for the first time right now, or even taking Calc 1 and Calc 3 is still a couple semesters away. This may look like, math, right? The subtleties of partial derivatives and uncertainty are very, very nuanced and very, very difficult. The general concept is not that bad. So please bear with me. It's going to look crazy because there's lots of letters and symbols you've never seen before. But I think the basic concept of this is not that bad, right? And you probably already understand these concepts. You've just never seen them put in terms of symbols before, all right? So bear with me here as we get into some kind of crazy symbols. All right. Anyway, as we talked about, we're interested in how much power is in the wind, right? This is what the wind turbine people call the resource. What is the resource? How much power is there? And that comes from this formula that looks a little bit like 1/2 mv squared, right? Because it's power and it's because it's, per unit, volume and stuff like that. It's 1/2 times rho, which is the density. This is the Greek letter rho, not a p, it's a rho. The area, right? How big is my turbine? And how fast is the air moving, right? This totally makes sense. Really dense air probably carries more energy with it. A really big wind turbine, with 90-meter blades, right, is going to collect more energy. And then how fast is the wind going, right? The faster the wind is blowing, the more energy it has. Okay, so these all make sense. Every time you see an equation, you have to look back and say, does it make sense? Now, one of the things it depends on is the area, right? How big is the wind turbine? Well, let's say the wind turbine, like the little toy ones that we're going to use in class, are 12.7 square centimeters, right? Or 0.0127. I guess that's not 0.12. Anyway, so some small area. However, we don't know this exactly because when I measured it, I used a ruler and I'm kind of eyeballing it and the blades aren't flat and it's hard to see exactly where the tip is. So there's some uncertainty. This little delta here means how uncertain am I in the area measurement. Right. It also depends on velocity. What's my velocity? We've been over this, 1.62 meters per second, but I don't know exactly if it's a 1.62. It's plus or minus 0.05 meters per second, right? This little lowercase delta. I've got a velocity, but I also have an uncertainty in velocity. Similarly, what's the density of my air? A typical value of density for air is about 1.19, 1.2 kilograms per meter cubed. But also, I don't know that, right? Now, it turns out this depends on temperature, and it depends on pressure, and it depends on humidity, it depends on a bunch of stuff, but I don't really know what my density is. I know within a pretty narrow range, 0.05 kilograms per meter cubed, or 50 grams for every cubic meter. That's pretty good, but I don't know. So, I can just take these numbers, and these numbers here, the top row, are what the high school kid would just plug into the formula and get a kinetic energy. So we call this the nominal value. I simply plug my measurements in and I get some nominal value. But I know that each one of these has a little uncertainty to it, so now I need to know what is my uncertainty. So how do we do this, right? It uses what we call a partial derivative. Again, those of you who are just now getting into calculus for the first time, you're probably, let's see, week 5, you're probably getting into derivatives. What's a derivative? But now we need to talk about something called partial derivatives, right? You'll learn about that in Calc 3, Math 234, but we're going to preview it now. The uncertainty in the wind kinetic energy that is due to the uncertainty in the cross-sectional area, right? Let's go back. Oh yeah, so I know my area. There's also some uncertainty in the area, right? I know area, but there's also some uncertainty. So now I'm saying the uncertainty in the kinetic energy that is a result of the fact that I don't exactly know what my area is, right, is this derivative. How much does, in general, what is a derivative? How much does something change when something else changes? So the question here is, how much does the power in the wind change when the area changes, right? And I take this slope, this is really just a slope, times, well, how much does my area change, right? So I'm taking the effect of area on the total power times my uncertainty in the total area, right? Similarly, the uncertainty in the power based on velocity is how much does my power change with a little change in velocity times my uncertainty in the velocity. And the same thing happens here. How much does the power change with a change in density times what's the uncertainty in the density, right? And so that'll give me some plus or minus. And if you're looking at this for the first time, your head's going to explode, right? This is a little delta. This is called a dou or a partial. We'd call this like partial W, partial V, something like that. All right. Now, all of you are probably familiar with this. This is actually not the Grand Canyon, obviously. I think this is the Sleeping Bear Dunes in Michigan. I didn't actually take this photo. I ripped it off the internet, which you shouldn't do, but I did. If you blindfolded someone and you stuck them right here, if you took someone, you're your best friend, and you put a blindfold on them and said, "Hey, how steep is the beach?" You don't even tell them you're on a dune. You just say, "How steep is the beach?" Right? And this person walks back and forth like this, right? They'd say, "Man, not steep at all. This beach is totally flat," right? So, which is true. How steep is the beach is not a very good question. You would rather ask them, "How steep is the beach?" If you walk, east-west. Actually, this is more like north-south. That's maybe why I called it Y. So how steep is the beach if I just walked north-south, right? Whereas if you pointed them the other direction and you said, how steep is the beach? And they walk this way, they say, holy cow, this is the steepest beach I've ever been on, right? So the question of steepness depends on which way you're walking. And this is the whole idea of a partial derivative. I can't just say, what's the slope of the beach? What's the slope of the beach with respect to y, or north-south? What's the slope of the beach with respect to x, east-west, in this case? Right. So how does a partial derivative work? I'm going to turn on my laser pointer here just so you can see a little bit better. I know that the kinetic energy of the wind, right, is 1/2 rho a v cubed, right? 1/2 times the density times the area times the velocity cubed. So the partial derivative with respect to area is the partial, the derivative of this stuff as this changes a little bit. The derivative of this as this changes. Now I know with regular derivatives, so this is my variable. So this is my variable. I'm not changing density. I'm not changing velocity. So all this thing here is a constant, right? And so what do? You take the power down by 1. Right, so this goes away. So the partial derivative of the wind power with respect to area is simply 1/2 rho v cubed, right? Just the constant remains, all right? So another way to think about this is so how sensitive is the wind power to the area? Well, it's 1/2 rho v cubed. This is how sensitive it is. Similarly, right, I could rearrange it this way. What is it with respect to velocity? So it's the derivative of all this stuff with respect to velocity. In this case, all of this stuff is a constant, and this is my variable. What do? I put the exponent out front, and then reduce the power by 1, so it becomes 1/2 rho a times 3v squared. So my partial derivative of power with respect to velocity is 1/2 rho a 3v squared. Right? Because this stuff is just a constant. I'm not changing that. It's a constant. Treat it like the number 6. Finally, I could do the same thing with respect to the density, and I get a result where the density just goes down by 1. The power of density goes down by 1, and so that means it just goes away. All right, so that is a very quick overview of partial derivatives. The pre-lab reading goes into much, much more detail, so I hope you give that a shot. All right. So now I've got all these uncertainties, right? I've got the uncertainty in power with respect to wind, or with respect to area, is the partial derivative with respect to area times how uncertain is it. So I plug that in here. And then I can plug in all my numbers. Now I know that based on the uncertainty in the area and all the other stuff, I know that the uncertainty in wind or uncertainty in power just due to the area is 0.0025 watts. Right? I can plug in the same numbers into the things I determined on the previous page. I know that the uncertainty in the wind power due to my uncertainty in velocity is this times the uncertainty in velocity, and I can plug that stuff in, and I get an actual value, 0.003 watts. Right? Same deal with density. I don't know my density exactly, so I have to take the sensitivity to density, multiply it by my uncertainty in density, and I will get some number. My uncertainty due to, my uncertainty in the total power due to the fact that I don't know the density exactly is this, right? And so for this problem, all components of uncertainty are important. This is on the order of 0.002 watts. This is on the order of 0.003 watts. And this is on the order of 0.001 watts, right? In many situations, one of them dominates, right? Why don't I know the power exactly? Why don't I know the kinetic energy of the wind exactly? It's because I don't know the speed, right? Whereas one of them dominates and the other two are tiny. But in this case, all three are about equally important. So I want to know not what's the uncertainty due to this, what's the uncertainty due to this. I just want to know what's the answer. What's the uncertainty? And the way we do that is kind of like Pythagorean theorem, or what's called root sum squared, or quadrature. And so I say the total uncertainty is the square root of all the individual components squared, right? How far is it from here to, I don't know, somewhere? Let's say, from engineering to my house. Well, how far is it west? How far is it north? And I take the sum of the squares and I get the total distance. Same deal with uncertainty here. So we plug all these in, and I know this is getting long. It's horrible looking at math over the PowerPoint. When I plug all this stuff in, at the end of the day, the power in my wind is 0.032. This is the nominal value. Where'd that go? 0.032. But I now can make a little bit better answer right here that I know it's 0.032 plus or minus 0.004. Right? So I've got a nominal value plus what's the plus or minus, right? So that's that. When we write this stuff down, right, and this kind of goes back to the Grand Canyon story. When I write this stuff down, I know my uncertainty is my power is 0.032 watts, and the uncertainty is 0.004 watts. A better way to write this would be 32 milliwatts plus or minus 4 milliwatts, right? So 0.032 plus or minus 0.004. Some of you will write this. Please don't be the person to write this. I'm going to see if I can get my pen to work here. Where are we here? This dumb thing. Screw that. Don't be the person that answers this way, right? It makes no sense to say, that sucks because I wrote all over it. I'm going to say it's 3 point, erase that. Do I have an eraser available? Yeah, erase the pen. There we go. So it makes no sense to say, I know that the age of the Grand Canyon is 5 billion and 16 years, plus or minus a billion, right? And that's basically what we're saying here. You're implying that you know this to the milliwatt, and then this one here would be the microwatt, and then you know it to like the hundreds of nanowatts, but at the same time, plus or minus 4 milliwatts, right? That's crazy. I'm implying with this number here that I know it down to this accuracy, this precision, but plus or minus something huge, right? That doesn't make any sense. You should not report it as I know it to 1 watt, right? I'm saying, okay, yeah, 0.032 watts. So this is or 1 milliwatt. I know it down to the milliwatt place. Plus or minus some incredibly small, no, that doesn't make any sense either. you should use roughly the same precision in your nominal value and your uncertainty. If I'm going to claim I know it to the milliwatts, you should say the uncertainty is milliwatts, right? So that's really, really important. Uncertainty bars, when you make plots of stuff, and we're going to make plots this week, when you plot a value, you should say, all right, well, I know the velocity is this, but there's some plus, these little bars here say, well, I'm not totally confident in that value. So these little bars, they should be called uncertainty bars, right? But a lot of people call them error bars. Well, if you knew the error, you'd fix it, right? This is an uncertainty bar, something we can't fix. There's a little plus or minus on the velocity. Consequently, there's a little plus or minus on the kinetic energy, right? So it's important to show this anytime you plot data, that it's actually not a point, it's a range. It's a range this way, and it's a range this way. All right. So don't forget, if you've made it this far in the videos, Lab 5.1, we're going to bend and break some stuff. Whenever you bend and break things, you got to wear pants, right? You got to be safe. You're going to wear safety glasses. You got to wear long pants. You have to wear shoes, not sandals. So yeah, this looks like don't come in your undies and barefoot. No, you wear long pants and closed-toe shoes. And you got to complete the safety form before you do that. Looking ahead for the rest of the week, 5.1 exercises I think are pretty good, but they're a little long. Yeah, they're long enough that to ask you guys to do this in one day or 1.5 hours is a little much. So there will also be no Friday lab this week, as you're going to be working hard on this. Please do not email your essay or me with every little question. Check Piazza first. Come to office hours and talk to us. It's a lot easier to say, well, this, and point stuff around than it is to try to write something really complicated in an email. Right? So come to office hours, especially on Friday, as you're working on this stuff. This is going to be hard. I'll warn you right now. This is going to be hard. Be prepared to come to office hours on Friday and get some help. Okay, that's it. Thanks for listening this far, and that's it.